Hello, everyone, and welcome to Electricity Canada's Conversation Series. Electricity Canada is the national voice for sustainable electricity for its members and the customers they serve. My name is Farhan Mirza, and I'm pleased to be your host for today's session. I'd like to first begin by acknowledging that the land on which I am broadcasting to you from today is the traditional unceded territory of the Algonquin Anishinaabe people. The Algonquin peoples have lived on this land since time immemorial, and I'm grateful to have the opportunity to be present in this territory. I'd also like to recognize Canada as the land of the First Peoples, Inuit, and Métis. I would like to pay homage to the Indigenous peoples past, present, and future that continue to work, educate, and contribute to the strength of our country. I would like to recognize that the land is shared through historic treaties, developed through contemporary treaties, and one that continues to be unceded territory. The conversation series features presentations from Electricity Canada's corporate partners, and the series will highlight a variety of Canadian and international solutions to current and future challenges faced by our industry. Working with our partners, these webinars have been developed to be of specific interest to those working in the electric utility space from generation through to the customer. For a list of upcoming sessions, please check out our events section on our website at electricity.ca. Before we get started today, I'd like to just go over a few housekeeping items. Our session goes from 1 to 2 p.m. Eastern Standard Time. A question can be asked, and we would encourage you to do so at the end of the session as they come to mind. So please feel free to type them into the Q&A function on your screen, and we'll ask them in the order that they are received. With that, we'd like to welcome electric power engineers to today's conversation series, who will be talking to us about renewable integration challenges. As the power system evolves with a higher penetration of inverter-based resources, or IBRs, it poses a great challenge for system operators and utilities to operate and maintain the overall system reliably. To understand the complex behaviors and grid vulnerabilities introduced by IBRs, an extensive effort in the low power system simulation area is required. The traditional phasor domain simulation studies are often insufficient in capturing the behavior of these devices, and hence electromagnetic transient or EMT studies are required to have a better insight into actual behavior in predicting the overall system performance accurately. Today's session with EP Consulting will dive into renewable integration challenges and possible mitigation options. And additionally, you'll be given a demonstration on IBR-related issues and practical solutions in EMT simulation platforms. Our presenters today, I'd like to welcome Ahmed Rashwan, Senior Director, Transmission Planning and Operations Utilities, Laleen Kotalawala, Associate Director, and Poria Estero, Senior Manager, Transient Planning, EMT. Gentlemen, welcome to the conversation series, and Ahmed, I'll turn the webinar over to you.
Thank you, Farhan, and thank you everyone for joining us today. As Farhan mentioned, I'm Ahmed Rashwan, Senior Director of Transmission Planning and Operations at EPE. And I just want to cover initially the webinar's agenda for today. So we're initially going to dive into renewable integration challenges at a conceptual level, talk about some of the challenges that we're seeing around the industry, and then dive into a few demos, one on model quality testing and another one on wide area simulations. Topics of discussion in this presentation will be, the increasing demand for renewables, solar and wind, but also batteries as electronic facilities across the nation. Some of the challenges associated with that increased renewable penetration, the different types of simulations that are required to be studied in order to fully capture the impacts of those different facilities, mitigation options and their effectiveness, and also how EPE helps throughout the industry. So the first point we did want to talk about is context for the presentation. So increasing demand for electricity across the country is going to drive need for new generation. We're seeing industrialization growth, electrification being part of portfolios across the nation. And in Ontario, for example, demand is expected to grow by 75% by 2050. That really does require an all the above approach to really getting to the finish line and meeting that demand. We'll see a lot of nuclear in areas like Ontario. You may continue to see some gas or hydroelectric in other areas, but renewables will definitely be playing a part in that supply mix. These are being pushed by several drivers, including environmental and policy drivers. And there are programs to support this, including carbon pricing and renewable energy incentives. And if we look at a couple of the examples for Alberta, for example, 2019 versus 2020, 2030 versus 2050, you can see that there is a large change in the supply mix or forecast supply mix with fossil fuels and natural gas playing a smaller role. Similarly, in Ontario, you'll see a diminishing role, although today it's already been diminished given Ontario had a fossil fuel reduction program through the coal attrition about 10, 15 years ago. So moving ahead to high demand for renewables, one thing that's driving that is the cost effectiveness of renewables. If we were to go back to 2010 when we had things like the feed-in tariff to incentivize some of these facilities, the costs were significantly higher. Now looking back about 10, 15 years and moving ahead to where we are today, those costs have reduced drastically. Solar, for example, has reduced fivefold in price. Wind has reduced by about 50 to 60%. And while offshore wind is about 50% of where it was in 2010. So significant changes in kind of the cost of these facilities and technological advancements also to improve how they interact with the grid. So if we were to go back about 15 years ago again, a lot of the wind turbines were doubly fed induction generators. Now they're full Type 4 facilities. The controllers have certainly matured and become more sophisticated, doing their best to mimic kind of the grid behaviors that we're hoping for to make it a more smooth transition towards a broader integration of renewables. So before we dive into the different challenges, it's important to characterize the differences between conventional generation and renewable generation. So conventional generation, typically characterized by synchronous machines, really large rotating masses of turbines and generators, high inertia, high short circuit current. Renewable generation, on the other hand, typically through high penetration of inverter-based resources. Power electronics really govern their behavior, low inertia and low short circuit levels. So we'll translate that into, impacts to the power system as we go through this. So for conventional generation, machine characteristics dominate the response. We talked about inertia of the rotating masses. The subtransient impedance really means that, that it has a high short circuit contribution, really strengthens that grid voltage at the connection point. The controls are governed by excitation systems and by governors and turbines. So let's take a look at one example of what this means. So when we look at frequency response, in the initial response following a fault, let's say less than 10 seconds, the inertia of those machines respond and release kinetic energy stored in the rotor and the turbines. And this provides a physical response directly to the change that happened on the system. Now, after that, governors will start to pick up and you get their control based. And what they do is they measure changes in frequency and then respond accordingly through a control system. That is in the secondary response. So that's still part of the primary response period, which is between 0 and 30 seconds, but on the tail end between 10 and 30 seconds. So we have this really robust transition from a physical response to then a control system based response, which covers the entire response period following a fault. Now, when we look at inverter-based resources, as we noted, they don't have inertia or inherent primary frequency response. And responses are typically required to be based on measures of frequency deviation. And those can be prone to distortion. We'll talk about that in a moment. Synthetic inertia, which we've heard of on the system, requires stored energy, so typically BES. We've also seen a little bit of that in wind turbines where they leverage some of that kinetic energy in the wind turbine blades, but largely BESS provides that active power. Grid forming inverters are available. We're hearing a lot about those. But broad implementation still has limitations. So how do they coordinate together? What are the right applications for them to be deployed? An inverter response can be really fast, which can be a benefit, but it can also be a drawback. It does require tuning when things are that fast. So, we talked about needing to take measurements to provide accurate responses. And their IBRs leverage instantaneous measurements, which in some cases can be heavily distorted during a fault or after a fault's clearance. Lots of harmonics involved, and the phase lock loop, which is the mechanism by which essentially IBRs, synchronize with the system, may not be able to track the sinusoidal waveform from the synchronized system when there are these distortions in that instantaneous waveform. So that can present some challenges. Another item to talk about is controller interactions. IBRs and electronic-based devices, including fax, can adversely interact with each other. They really are software controlling the electronic hardware, and depending on the settings that you've implemented, they can chase. So a system disturbance can trigger these types of interactions. And one example is if you have an existing facility well tuned for that system, and then you integrate a new facility and maybe well tuned for the system without considering the existing facility. But once you put them together, they can interact with each other. And we actually have seen this and have performed analysis for it in one of the states we operate in the south. And they had a wind farm that was initially integrated. Everything looked great. The wind farm was incorporated, and there were oscillations observed on the power system due to controller interactions. And a StatCom was implemented to manage that interaction at the new facility. So certainly something that, although we can talk about it in theory, it is something that we experience on a day-to-day basis on the system as renewables increase their presence. Another point is recovery in weak grids. Canada is a large country. In many cases, some of the renewable facilities are connected in more remote areas, supplying power to the load centers. And so those parts of the system typically have weaker connections. And following a contingency event, the short circuit level at that point of interconnection may be significantly reduced because of the change in system topology. And in some cases, IBRs may not be able to stabilize after that fault clearance. And so what we actually have here, just as an illustrative example, is a situation where a wind turbine struggled to stabilize after a fault. And you can see that at the top graph. And that was due to a low short circuit ratio of about below 3. Once you put in a compensatory mechanism, such as a StatCom, that actually increased the short circuit level on the system and allowed it to recover appropriately with the controls in place. We talked a little bit about this, but dive in a little bit deeper. So in weak grids, large angle jumps are very possible. And as we noted before, the synchronizing mechanism for inverter-based resources is that phase lock loop. And if the phase lock loop cannot track the waveform on the system, it's unable to properly appear to be synchronized. In some of these weak grids, the change in voltage experienced for a change in reactive power, delta V, delta Q, can be really high. And so you'll see these types of changes around the system. And so what we need to consider, in particular for these areas, is if you do have a generator, and most of them will be in voltage control, if they are injecting Q to compensate for voltage changes on the system, doing so very quickly, which is within the capability of IBRs, can be detrimental depending on the short circuit level. So in some cases, controllers may need to be slowed down, which could adversely impact, other aspects of their performance, such as quick correction of voltage change. But it really becomes an art to tuning the controllers to adapt to the area where it's connecting. So that's just an overview of some of the challenges that we've seen. We want to dive into some of the simulations that we perform, typical load flow and short circuit analyses, um, transient stability studies, electromagnetic transient studies, small signal analyses, distributed system simulations, and protection system simulations are things that we perform on a regular basis. Today's focus here is really on contrasting the difference between, your transient simulations in the phasor domain and electromagnetic transient simulations. So moving ahead here, what do these look like? So the phasor domain is a positive sequence equivalent of the power system. So you'll see basically a single representation. And the tools typically used in this area are PSSE, Dixielant, PowerWorld, while EMT simulations show all three phases. PSCAD, EMT, DC, EMT-RV is also another simulation platform, as well as ATP, among others. And so that really is the difference. One, you see all three phases, instantaneous values, whereas for the phasor domain, you're seeing an RMS value, a positive sequence equivalent. So moving ahead on applications, when are phasor domain studies appropriate relative to EMT? So, right now they're widely used by transmission system operators and independent system operators, and they model really large areas with really good simulation speed. Typically, they've been suitable for conventional systems, so mostly, where we were before. And there is a trade-off on accuracy. So they don't fully capture the impacts of IBR. So if you're looking to see rotor angle stability, transient voltage drop. Those are things that you can still capture well in the phasor domain. However, the controllers and control interactions, subsynchronous phenomena that we talked about a little bit more, and we'll dive into more for going ahead, that really does need a more refined look at what's happening on the system. So for that, if you're incorporating HVDC or fax devices, you've already used PSCAD or you've already used EMTP-RV or any other simulation platforms to properly model those facilities. EMT allows you to accurately model the really quick response of these electronics and that chasing that can happen between them. Captures system dynamics properly. There is a little bit of a trade-off to get that accuracy. There's a higher computational intensity required. So some of these PSCAD studies or EMT-PRV studies or ATP studies can take longer. EMT simulations are very detailed and require a longer simulation period. So what you do in this case, rather than having a full system model like you might in your phasor domain studies, you have a reduced model which accurately captures the dynamics that you're hoping for. So you put together a system equivalence, and Lilian will cover that in his demonstration of the wide area studies. And the good news is for EMT studies at this point, the simulations and the models have become a little bit more mature. So EMT models, although more detailed, are in fact readily available. So EMT simulations for IBRs, what we've seen for single machine infinite buses, ensuring that the control behavior is good, analyzing potential weak grid responses, what that could look like, and assess the ride-through behavior and the frequency response behavior of these facilities. And that's something that Poria will cover in his demonstration. Wide area EMT simulations, again, which will be covered by Lillian. It looks at potential controller interactions, ferroresonance, torsional interactions with nearby generators, and resonance on the system. You can use them to determine whether your models are properly tuned and stable for that big system integration. Analyze that and the impact of network dynamics at a higher level. And for systems with high IBR integration, electronic devices and HVDC, really making sure that when you look at a broader area, you're really covering those potential interactions between that variety of facilities. In many cases today, EMT simulations are limited to single machine infinite bus just to do model calibration. As folks start to expand into that wide area simulation, those dynamics, when they do their first set of studies, are going to be the first time they have an appreciation for those interactions between the different electronic equipment. So it's really important to make sure we have good models for IBRs, fax devices, and HVDC to capture those interactions. So for large area EMT simulations, so countries and regions that have developed large area networks and in PSCAT today include in Canada, Nova Scotia, Ontario, New Brunswick, and Alberta. Australia has developed a full system model. The AEMO has one that was implemented recently. In the US, Texas and Hawaii have put in full system models. National Grid in the UK, ELIA in Belgium, and in Denmark as well. However, there's hundreds of transmission system operators and ISOs that performs EMT studies today at a more reduced level, looking at that equivalent system equivalence. So we've talked about challenges, we've talked about modeling. Let's talk about some of the mitigation options, apologize. So for synchronous condensers present an option to increase system strength. So for both for frequency and voltage stability. However, they do come at a high cost, and there is a lot of push for them at this point to be included. So what you're finding is, there's low availability overall in the industry. Modern synchronous condensers do have really high inertial constants relative to the more traditional ones. So they are quite grid strength. They really do strengthen the grid. An example is in South Australia, they deployed synchronous condensers across the system to strengthen the grid. In Texas right now, they're looking to do the same thing in their Panhandle area, in their Northwest footprint. And we know from what we understand, Nova Scotia is planning on wind farms being accompanied by synchronous condensers in the future as well. Battery energy storage, great solution for energy balancing for some of these facilities. And we talked a little bit about grid forming BSS as being something that can help with system strength in the future. One thing that is important to understand with grid forming today is that coordination principles have not been fully established yet. So it's still kind of in a nascent state on how to properly integrate them into the grid. And so while we do believe that there is going to be a strong future for them, those principles need to be outlined first. So that's something that we do look forward to seeing in the future. Other mitigation options, which are quite common, retuning IBR control parameters is something that, we've seen and we've done before. Introducing power oscillation dampers or power system stabilizers. This is actually a pretty important one. We had observed at one of our client territories oscillations on their 500 kV system, ranging from 490 to 580 kV. So really broad range of oscillations. Sometimes we were surprised that the system stayed together with that magnitude of change. And what had happened was facilities were integrated piecemeal, as we noted before, without proper coordination. And so what we helped them design and then implement was a power oscillation damper for a quick responding SVC on the system. And that helped reduce kind of the variability of the oscillations observed to something closer to about 430 to 445 kV, and then some fine tuning at the IBR controllers in that area reduce it to a fully manageable level. So overall, we're happy to be part of that, but just showing that power oscillation dampers can be very effective. So we've talked at length, and we're looking forward to going into some of the presentations. Before we do that, we just want to introduce EPE to the audience and talk a little bit about how we're organized and how we help overall. So EPE is an organization that was founded in 1968, headquartered in Austin, Texas, with 520 employees. Really proud to report that we have 140 employees in Canada across 9 provinces. We have 2 offices in Canada, one in Mississauga area in Ontario, and another one on the University of Waterloo campus. We're divided into 3 different business units, one supporting utilities that's fully ring-fenced from our energy resources team that supports developers. So we do have that full separation between those parts of the organization, as well as our software solutions team, which has developed platforms for siting of generation and also automation of studies, which we're really looking forward to advertising a little bit more fully once we have that further along on the development process. For my team in particular, the one leading the transmission studies for utilities, we have over 80 power system engineers. We work with 6 ISO RTO clients directly and over 40 utilities. One staggering stat that we put together recently, I'd like to include it on this slide, is we've performed up until July 31st, 75 gigawatts of large load studies. So that just tells you that, the push on the system. We're talking about IBRs today. Another major shift is that large load inclusion on the power system and really honing in on their impacts. We're leading the Energy Systems Integration Group task force on performance requirements for large loads. I know Alberta recently put out a set of requirements, which was encouraging to see. And so we're looking forward to seeing more of those come out and be part of that, informing those requirements. In terms of kind of the studies we offer, we've got them listed here. Ranges from generation to load interconnection, long-term planning, regulatory studies, root cause analysis, operational studies across the gamut of studies that we've mentioned in the middle. So steady state, short circuit, transient stability, electromagnetic and geomagnetic. Diving into EMT, which is a key topic for today. We've supported interconnection, wide area network studies, HVDC studies, and high frequency transients. With that, I'll pass it on to Poria.
Thank you, Ahmed, for that. And let's share my screen. As Ahmed mentioned, talking EMT simulation is a need in many studies today. But where we can start? Before going to that more complicated wide area EMT simulation, we should make sure that every model that we have adding to that the system is working correctly. There are grid code requirements that about the performance feature of each model. And here we are shortly show how we test the model before using that and making sure that all the feature and performance working as expected. Here I have a few example All of them is include this green part, the IBR model. Normally they are black box. We don't see that exactly how the control inside that is acting, but we need to check the performance of them. So there is some input setting, some measurement go inside that in the PSCAD model, the cable, transformer, internal, the plant, and then connected to the POI. And in this type of single machine test, we have a one voltage source here, controllable voltage source, and want to see the different reaction of this model without looking inside that in response to that some change. I make that very simplified version here, just to sake of the demonstration. And here we have a voltage source. As you can see, this is a simple switch here. The voltage go from 131.8 to 131 in 5 seconds. So I have the result here. You can see that the voltage RMS go decrease suddenly. And what we can see and what we expect here, we are testing here to see this IBR model can produce the good response in the reactive power or not. But we expected that active power should be remain same. And this is a small voltage change, and reactive power should go up. And we can see here that exactly having this behavior here, that the reactive is starting to get more to contribute in the voltage regulation. At the same time, it's required we look at that the ID and IQ of that to see that they need to be almost the same, because the voltage came down and we want to have the same power, so ID is increased a bit and IQ it's increasing. And the frequency oscillation and all these things that PSCAD shows is that based on that how we measure that's this noise in the practice based on the measuring method, we can see that even in the practice that normally we don't see in the RMS simulation. Same, we can do the same test for the frequency change. We have that the same setup, but this time the frequency go up just a 0.3 hertz. And we can see here jump in the frequency measurement, we will see that. And the expectation is that the power having the reduce, this is the frequency response of that this IBR, and that's after some delay. There was a question in the Q&A, so you cannot count that this inertia is a frequency response. It has a delay things in this model. And then we can see that the same behavior, the Q should not change. And we will see that the ID going down, IQ remains same. This is the behavior that we expecting see. We have that the full all the instantaneous current and voltage here. We can see the change. Maybe it's not very clear in this test, but we can see all of these things here. I will jump to the another test. We need to have an angle jump test as an example. When we have an angle jump, that's kind of working how PLL working well or not, we can test here. You can see the source angle is changing 30 degrees. And you can see that in the instantaneous voltage and current, we have this jump, obvious. We can see the expected result, the power should not have that much any change here. And also the reactive power. So it goes as expected. There is a some here because the angle is changed. Again, need to that PLL find the lock to the new phase, but it's going well. And there are some frequency measurement error that is happening in the reality as well, because that depend to that the method that you measure the frequency. Again, that's caused some of the problem for the real world cases that angle jump could if, for example, this frequency changing, creating some protection or some other devices activated. The frequency, real frequency is not changing, but the measurement method show that. And it's something that we can see in the EMT, for example, simulation, and we cannot see in the RMS simulation. We have this, now I have a bit more complicated test. I wanted to have LVRT, low voltage right through capability of IBR. I changed the voltage magnitude with this profile, and then wanted to see what's happening for the power. As we expected, when the voltage goes zero, so the active power and reactive power go to zero. But here in ID and IQ, we can see better because active and reactive is at the I times to V. So when V is zero, active power is zero as well. But what we expected that when there is a voltage go to the zero, IQ should go to the maximum amount to try to inject more reactive power to support the grid. And then this reactive power going up, after a while, the voltage recovery, the active power started to do because reactive, when it's coming down, active has more room. Here is the priority of the controller. Inside here is the Q priority. So we can see all these features and all this performance by doing this kind of simple test to make sure that what's the behavior. For example, even we back the voltage to the 0.98 per unit to see that, for example, LVRT loop, it's not freeze. It should be back to the lower value of reactive power. So all this performance need to be tested before we started the doing the test. Similarly, other type of tests like the fault, I have here putting a fault, see what's happening during the fault, how does the active power and reactive power injection be changing. And we can see all this from the RMS value calculation or instantaneous value that we have all here. So I just wanted very quickly show the steps that as a starting step before doing any kind of a more detailed EMT simulation. And now hand over this to Lalin to talk more about steps in the wide area.
Yeah, thank you, Pooria. Let me share my screen here. So I think Ahmed gave you a nice introduction to the where the IBRs and related challenges, and then and also the where the studies should be heading to. Pooria gave you a kind of introduction. I mean, the preliminary stage of the studies may be to collect good models and check them and ensure that's a proper replication of what's in the field. So once you have the these models, I mean, the next step may be to do some kind of wide area studies we call in. Why we are doing mostly in EMT, because we all know that EMT can capture more information and more correct behavior of the IBRs. Therefore, it becoming popular now to perform these kind of studies in EMT platforms. And people have convinced that the EMT shows mostly of the cases the whatever they have seen in practically in the field. So
Lalin, before you go too far, we can't see your screen just to make sure you're sharing that. Thank you.
okay, sure. Yeah. I think now you guys can see my screen. Yeah?
Perfect. Thank you. Go ahead.
Yeah. Sorry. So for that purpose, I mean, I have here a small demonstration case where we can see how this wide area network studies works. Generally, these kind of studies, these models can be sometimes hundred buses, sometimes can go to thousands, even in EMT background because of the recent development in EMT areas. You can use a multi-cores in computers. You can divide EMT system models into small pieces and push into these cores, and then you can run simulations much faster compared with the technology maybe decades ago. So for demonstration purpose, I have like a relatively small model here for the demonstration purpose. But as I said earlier, even Ahmed talked about this, some of the areas in the world, people are doing like a full-scale EMT wide area network studies. Generally, this kind of model may capturing a part of the or sometimes a full model, or sometimes a part of the actual physical area or actual power system. So in those kind of cases where you're capturing is a part of that, definitely you have a detailed model where you investigate your suspected issues, and also you have a boundary connected to the rest of the system. So at the boundaries, you can see here in this even the small case, we use equivalent source at the boundaries. If you see the right side here, and then you develop several buses. I mean, depending on how far you want to investigate. This is again, I have to emphasize, this is a small model, but in practically we develop very large models. Then you capture few of these dynamic devices in this study area. You see, I have a synchronous generator here, and also I have a wind turbine connected to this particular bus. So this wind turbine generally, I mean, again, as I said earlier, the EMT studies take too much computational burden. So normally we break into any of these kind of EMT studies in small pieces. In this case, I mean, simply I have divided into two, the network model, and I push the wind turbine model to another case here. So they are physically linked through a natural place to break this is generally a transmission line. In this particular case, I assume there is a small overhead piece between the wind farm and the network, 6 kilometers here. I use that as a nice natural place to break the network and the wind turbine or wind farm into two different cases. So we can combine like that. You can combine as many as cases together, many IBRs together, and run as a one unit. That facility is there. I mean, I know that in Australia they are doing 100 of them together, pieces together. So that's possible now. So so this is just a demonstration of such kind of big effort. I mean, at the very beginning you do like this. So in this particular case, at the network, this is my POI bus. I have connected, as I said earlier, the wind turbine, which is actually consists of 10 units, each is 5 megawatt, basically delivering around 50 megawatt. If you carefully look at this network, which is actually representing a very weak system, purposefully for our studies or demonstrations, out of this, at the POI, you see that the two lines connecting to the POI, the one at the top, as you see here, and there's another bottom one, a short bisection, and then they're connected to another bus through 65 kilometer long line. So there are two paths. Due to some reason, excuse me, due to some reason, if there's a fault on one of these lines and you drop the line, the short circuit ratio at the POI dropped drastically. As a result, there may be a challenge for wind farm to recover after fault clearance. So I have already run the simulation. We will evaluate what's happened here. At the very beginning of the simulation, everything is fine. As you see here, up to 5 seconds, where both the lines are available and they're in service. At 5 seconds, what will happen? There will be a fault here, and you open the breakers and you isolate the line. Now, as a result, there's only one line connected to the POI, so the POI short circuit ratio dropped drastically. When we go back here, the same thing you can see at 5 seconds, there will be a fault, the voltage dropped drastically. And then fault cleared and voltage tried to recover at the POI bus. All these measurements are the close to the PO bus or the inverter bus. Either, I mean, we can analyze through either measurements. So you see that the whole wind farm is having a struggling to recover. I mean, you see that there's no way that the wind farm is triggering. I mean, the recovering, probably after some time it may be tripped permanently. So it means this, after this contingency happens, whatever the resultant short circuit ratio under that condition, the wind farm cannot recover. So if we think about what could be the solution, one solution could be adding a system strengthening mechanism, we call it. The good example would be a synchronous condenser. So I have already made an example synchronous condenser here. Right. I will add a synchronous condenser, which is around 20 megawatts and 20 MVA. The plant is 50 megawatt, the wind farm is. So let me enable this and run the simulation, and then we discuss the rest here. So as you see that this simulation is after fault clearance is unstable. Let me run again with the synchronous machine placed there. While the simulation is running, I will just a little bit talk about the synchronous condenser. As you see here, there's a synchronous generator, which is basically in PSCAD in modeling perspective. We have the synchronous machine and the exciter up there and the governor turbine arrangement at the bottom. So it is the real replication of the actual synchronous machine and controls. When I go back to the synchronous condenser, simple model here. Actual models may be a bit complicated with the control point of view, but understand the concept, basically what happened in synchronous condenser is that you are missing the turbine part or the prime mover part, right? So there's no torque coming from outside to the machine. So as you see here, I completely disabled the turbine and the governor part and added the just zero torque here. Basically, there's no torque coming to the machine from any external prime mover. So this can be a simple synchronous condenser. Generally, the one thing, if you're dealing with these kind of things down the road, generally the exciter systems are a little bit slightly different. Sometimes the machine characteristic can be different in sync condensers, especially special purpose sync condensers. So we have to pay attention on those. But for understanding purposes and this kind of learning purposes, we assume this kind of arrangement is very good. So let's go back to the simulation. It has been run now. As you see here now, I mean, because of the deploying the synchronous condenser, now you see that after the same contingency situation, the voltage recovers very well, and the plant could be able to send the full power. As you see here, there is a 50 megawatt now flowing into the system. So this is a very simple example. We can demonstrate what could be happen in the real system, wide area network. Actually, once you're having many IBRs and many renewables together, the interactions may be much more complicated than this. And you can see and you can look at for mitigation options. As Ahmed said, there are several mitigation options people are looking for. I mean, system strengthening using synchronous condensers or battery or grid forming batteries, combination of these. This all line in evaluation. And also sometimes you can retune the parameters of existing plants and make more them harmonized to the system requirements. Those are the things you can look through these kind of simulations because you have the access to all these I mean, models of all these IBRs in the same wide area network model. So you can go to the plants and look at the parameters, and you see that if you have good knowledge, I mean, which parameters affect with kind of performance. You can change them and see whether there's any improvement. So this would be a nice insight for any ISO utility, especially they want to do this kind of evaluations as an overall system. I mean, as Pooria said, any of these individual IBRs, wind farm or solar or BESS may be performing very well, but nobody knows how they perform all together in the system. So therefore, I mean, there can be interactions, there can be some system conditions give them the bad performance. So therefore, I mean, it's important to do this kind of wide area evaluation, especially if you know already, I mean, there can be some physically observe some of the oscillations interactions, or you know that this particular area is very, very weak and there are many IBRs coming in that particular area. Those are the places where you can decide, I mean, you have fast track, in other words, these kind of studies. You don't want to go to whole system, I mean, at the first instance, but you can start part by part, looking at the problematic areas or very, very weak part of the grid, and then go into the rest of the system at a later stage. I mean, because RMS studies will give you some kind of background or some kind of knowledge for you guys on overall system behavior to some extent, but this is beyond that point. I mean, where you can have physically see the problems, or you know that this particular area can be really weak. Those are the two starting points, I think, for the EMT studies. With that, I think that's all with me presenting. I give back to the Farhan.
Excellent. Thank you very much, Lillian. That was great. So with that, I think we're transitioning to our Q&A section. We've got some questions coming in already, which have been answered during the presentation. So thank you very much for that. And we'll open it up to the audience for more questions to be asked. We have about 10 minutes or so that we can ask our presenters. Just to maybe kick things off real quick. And anybody can take this first question. Have you seen real examples of renewable integration challenges on the system, and how did you approach resolving them?
Yeah, I can speak to this, and I'm sure Lillian and Poria have as well. We noted one of the examples in Texas that we saw recently. Maybe I'll just dive into that one a little bit further. Oh, are you able to still see my screen, folks?
No, you can reshare your screen if you like. Yeah.
Okay. Apologize for that.
No, you're all good.
Um, all good now?
Not quite yet. There we go. There we go. It's coming in.
Perfect. Okay.
Yes.
And so, in that particular example that we had, we talked about two different facilities connecting nearby. We've had a similar situation where, a facility had connected, not necessarily as close as we expected to a series compensation device, and initially didn't make it through the screening to be included for a series compensation type study. And then after that, through actual experience on the system, there were a set of cascading um, outages that occurred due to kind of a large scale storm that came through. That facility actually ended up experiencing, so the system actually ended up experiencing subsynchronous resonance because of the system configuration with the facility radial onto a series compensated device. And so that was something that we went in to support with, put in operational procedures to make sure that if there is that danger, that there are disconnection opportunities. Another one we did recently was a new facility had connected with a, I guess, relatively large transformer to the HV system. With that, there was an instance of ferroresonance that was observed on the system. They took some manual actions to disconnect, but they didn't want to do that going forward because there could be equipment damage as a result of ferroresonance. And so what we helped that utility do is put together an automatic detection scheme through a ferroresonance relay There was one available in the world somewhere in Europe, and we were able to bring it in. We went into the field, tested it out, made sure that it would work through some testing procedures as well as through some tuning, so with Comtrade files and everything. And then after that, we were able to put that facility back in service with that protection in place. So yeah, certainly we've seen a whole slew in practice, and also obviously we try to do them proactively when we can in our simulations.
Right on. No, that's great. Thank you for sharing that. We've got some questions coming in from the audience now. So I'll ask them in the order that they're received. So Hillary asks, to solve the instability problem resolved by the SyncCon, can it be replaced with BESS, and what are the financial implications?
So I think, and I'll pass it on to the team, but I think I'd start off by saying the synchronous condenser adds short circuit capability to the system. It really does strengthen the system. BESS, and Poria will probably jump in on this, as a grid forming, it can help, but it doesn't actually have inherent inertia with it. It doesn't inherently strengthen the system capability, but it tries to mimic that. So I'll pass it on to Poria for a more detailed answer.
I just want to add that one thing that in synchronous generator is very unique is that the capability of that providing the current, for example, 5 per unit current in a short time, like in the fault in any type of inertia response. When you do that with the BESS, even if you call that invariant, that's the limited to the 100%, 1 per unit or 1.5 per unit, for example. It's not related to the 5 per unit or 2, 3. You can definitely do this type of things, but it's not completely 1 equal 1. You say that 100 megawatt BESS GFM is very equivalent to 100 megawatt for example, synchronous condenser. So each of them, they have their own specification or challenge, and maybe from the economic perspective, BESS can do the other things. Then if provide something beside that, then we are more than happy. But synchronous condenser is just for that, providing this inertia or system strength. So then it's need a technical and economic consideration both together. I just want to add these things.
Thank you, Poria. That's great. Next question is, I'm curious if any studies have been done that have large loads, particularly data centers within large IBR penetration areas, and what were the challenges, experiences, and lessons learned?
Great question, and good to hear from you, Snaps. And so I think for this one, it's new territory. We have been developing a PSCAD-based large load facility model to be used in wide area studies. However, there isn't necessarily a good set of models to be used that are kind of foundational. So we've done some things by inspection. And I think the same challenges that we mentioned for IBR integration exist with the loads that are also electronic based. There could be interactions between them. Some of those data center loads are highly variable, so they inherently introduce oscillations to the system. Those can interact with some of the facilities nearby. But more so than just with IBRs, they can interact with synchronous machines. So with the oscillations introduced by AI data centers, they can actually introduce torsional interactions on the shafts of some of the synchronous generators that could be nearby. So when you hear about co-location and it kind of being the way to manage the demand that's coming from some of these AI facilities, leading the ability of the grid to actually build infrastructure to supply them, it's something that's really important to look into is, are there potential torsional interactions with the AI characteristic load and the facilities that are serving them?
Awesome. Thank you, Ahmed. Next question is from Grant. Do you have any rules of thumb about how many or how large the IBRs have to be before you need to worry about effects like these simulations?
Laleen, do you want to take that one on?
Yes, sure. There's no actually, first of all, rule on this. First thing I have to say that. But the people have different approaches. For example, I mean, the one thing is, if you know that these kind of plants coming in, you weaker part of the system. I mean, it doesn't matter. Your system can be very strong, but the Australia we have seen, in especially Queensland and some areas, the actual renewables come in a weak part of the system. Then you have to do the studies. Even though your grid is very strong, if renewables are in a weaker part, when I say weaker part, normally we are talking about the SCR is lower than 5, or some people say 4, 3 or something. 3 obviously, yes, you have to do, but SCR is around 5 or lower than 5. Probably you have to do start putting some studies. And the other way, I mean, what we have seen, for example, in South Australia, your penetration level is so high, like you have penetration around 30, 40, 50%, or sometimes it can go 80, 60, 80%, that kind of values. There's no rules set honestly yet, but people are looking at how to start with this. Obviously, you have to take care of your weak part of the grid, and you have to look at where the penetration is. I mean, overall system penetration goes high. Or thirdly, if you've already seen some problems, I mean, practically, I mean, some oscillations, some interactions, then you should start the studies. But I have to add one more thing upon that. Most of the places people see this problem in the latter stage, but at the very beginning, people, as long as you don't see problem, you don't collect the models. So the most of these places, the problem will be that the situation comes to do the studies, you don't have the models. So it is important years before you see or you anticipate these kind of problems, or you see a high penetration, you have to collect the correct RMS and EMT models, because down the road, if you see any place, you see that the grid is very weak, or there's some interaction, practically you see that, you have the models, you can develop the overall wide area network, and you can do the studies. So that's also important point to keep in mind. I mean, at least even you don't see these kind of issues right now, to collect good models.
Yeah. And maybe just to build on this, I would say, Grant, even if you have two facilities, but they're in close proximity electrically, you probably would be it'd probably be better to just do the studies to make sure they're not chasing each other in terms of their control system. So there could be those interactions. So in terms of rules of thumb, I really do think it's potential for interactions between the facilities with their control systems. So if they are relatively far apart, you may not have as high of a risk. But if they are clustered together in an area, or electrically the distance is short, in addition to kind of what Laleen mentioned about short circuit, I think that's another thing to consider as well when you're determining if you need to go ahead with these analyses.
Awesome. Thank you, Lillian Ahmed. Final question. I think we have a couple minutes, so we'll ask that last question from Huck. How likely is it that electric vehicles through vehicle to grid or other smart charging strategies will play a significant role in grid stabilization within the next 5 years?
Yeah, I think it really depends on the magnitude of that combined impact of the electric vehicles, and how well that can be coordinated with grid needs. So as of today, it's very decentralized. It's residential or commercial level, very little visibility and control into that from the overall grid perspective. I think to provide a role in grid stabilization, there'll need to be an aspect of coordination with the grid needs. And that's, I think, something that, as potential platforms come into play where the distribution system can interact more with the transmission system, that those types of models could start to contribute to solving some of the issues on the system.
Excellent. Thank you. Thank you to the audience for all your questions, and thank you to all our panelists, Ahmed, Laleen, and Poria for taking those and running us through the presentation. I think it was great. Unfortunately, we've run out of time, so we'll conclude there. I just want to remind everybody that all of our future events and webinars can be found in our monthly newsletter on current affairs, or you can go to the events section on our website at electricity.ca. Any final words, Ahmed, Laleen, or Poria, before we sign off?
No, thank you for the opportunity for us to speak to the audience today. We really appreciate it. And if you have any follow-up questions, please reach out. We're always happy to have a conversation.
Excellent. All right. Thank you once again. Thank you to EP Consulting Electric Power Engineers for presenting today, and each of our audience members for joining. Until next time, stay safe. Bye for now, and we'll see you next time. Have a great day.
Thank you.